All right, so yesterday we were looking at a circle and dealing with the circumference of a circle. We were interested in finding, let me just hide some stuff here real quick. We were ultimately interested in finding the length of that blue arc, correct? Okay. Now, what we ended up doing is writing a formula that incorporated the angle or the arc measurement. So let's say, I don't know if I can get this to go to the increment that I want. So just hold on a second. Go 5 degrees. Okay, so if I make that 60 degrees, that angle, that central angle we said was 60 degrees, what do we consider that measurement out there for that arc then? Also 60 degrees. That's that one-to-one relationship that they're the same. Okay? What that does, and if I were to take that blue arc, and I replicate, how many times will I have to replicate that blue arc, or cut and paste it, so I get to 360? 6 times, right? Okay? So to figure out that that blue arc is 1/6 of the entire circle, we are always going to take this formula here. X over 360. That will generate what portion, what percentage, or what ratio of the circle your arc is. Does that make sense? Okay. And then because we're talking about circumference, it's finding arc length, and arc length is just a portion of circumference, we then need to multiply by 2 pi r. Okay, so if I read this, it's basically saying what portion or what percentage of, because that's what multiplication means, right, of circumference, okay, is your arc. So that is arc length. Okay. And we did several questions about that yesterday. To be honest with you, I don't think anybody's going to have too big of an issue with just coming up with arc length. Okay? I think what we do today is where most of the issues arise with dealing with circles and these particular measurements. Okay? But that is arc length, and as we move this around, obviously we can change that arc length. Right there, what would my percentage be? What would, yeah, it'd be 1/2, right? 50%. Okay? So I take that 0.5 and I multiply by my circumference, and that's going to give me that semicircle, right? Okay. What would happen if I got out to here? How big would, now it disappears, but what would that arc be? What would that percentage be? 360 over 360 would be 1, right? And then hopefully you realize, well, that would just give me 2 pi r, which is just the circumference. All the way around is my circumference. Okay? Is that okay with everybody? Okay? All right, now what they like to do, this isn't always the case, but they like to give you values of that angle that divide with 360 nicely. Okay? But that doesn't always have to be the case. It can just be any random value that we want between 0 and 360. Okay? Today, what we're interested in is dealing with that red shape right there and finding its area. Okay? Now, how many of those red shapes do you think I could fit into that circle to complete the circle? 6 of them again. Okay? And it's because the angle is 60 degrees, right? 60 degrees goes into 366 times, right? So that red one is 1/6 of my entire circle, right? If I want to find the area of that, okay, what's the area formula for a circle? Pi r squared. Okay? Pi r squared. So if that red region is 1/6 of the area of a circle, can I write 1/6 times pi r squared? Does that make sense, everybody? Well, it doesn't have to be 1/6. What if it was? What if it was something like that? That would be what of my circle? 1/4. Okay? And we're seeing that 1/6 or that 1/4 being generated by taking that angle and dividing it by what? 360. Okay? And when I say that angle, I'm either saying I'm taking the angle and dividing by 360, or because the arc is the same amount, it'd be the arc divided by 360. So now if I want to find the area of now this region is called a sector. Area of a sector. It's still x over 360 times, now instead of circumference, we're now talking about area, right? So pi r squared. So we're multiplying pi r squared, multiplying your area by a number between 0 and 1, and that's going to then give you the portion of the circle's area that you're interested in. Okay? On our test, I will most likely give these to you. On the end of course exam, okay, and I'm going to send this, now not all of you will come see me during the end of course review for Wildcat time. At least some of you go to Mr. Malk's class one of those days. But I will give you this at some point in the next couple of days. But this is the reference sheet that you guys get on the end of course exam, and you do not see these formulas on there. You see some formulas. You know, obviously we've dealt with the distance formula a lot. It's nice that that's on there. If you need a factor or anything, that's on there. Okay, you got your volume formulas here on the right, which we'll talk about next week. You've got your area formulas here of some key things. Okay. So these formulas will be. Now this is the reference sheet that they give you. It's got your 30, 60, 90s and all that kind of stuff as well. But this particular specific formula, where'd it go? That formula right there, when I got to multiply by that x over 360 to the pi r squared, will not be on there. Okay? So that reference sheet, when they give you that reference sheet, guys, and this is the case no matter what, whenever you get a reference sheet, it's a benefit to help you, but it doesn't necessarily mean that those are the only formulas and expressions that you're going to need. Does that make sense? Okay. With these types of problems, okay, it's pretty cut and dry with just finding the area of the sector. They're going to have to give you your arc measurement somehow, whether they give it to you as a direct, here's the arc measurement, 90 degrees, or they give it to you as a central angle and you have to transfer it. They're going to give that to you. They're going to give you your radius. Okay? You just have to then plug things in and then use your algebra, order of operations knowledge to reduce things. Okay? So let's do a couple examples of this, and then we will kind of talk about a little bit more difficult of a problem that is usually going to pop up with this idea.
Do you have to use the arc length to find the area of the section?
No, you use.
You have to find that first.
It's just a different. They're just two different things they might ask you about. They might ask you sector area.
So you don't have to find one particular.
No. There will be, later on, and this will be in May if we get to it, but it might be, when you take trigonometry, they might give you information they might tell you that your arc length is, let's say, 45 pi, and they might give you then the task of coming up with the area. Well, when they give me arc length is 45 pi, we should be able to set that equal to our formula for arc length and kind of work our way through and find the radius so that we can make that radius and turn that radius into an area. But that'll be later, and that won't be on the end of course exam or anything like that, but that might be something we do later. That's in Algebra 2, college algebra, trigonometry, they like to give us, instead of, they hide here in geometry, they hide components to your formulas and stuff like that through geometric facts. As you move into other courses, a lot of times they like to hide variables inside other quantities. Kind of, if I need a radius, they might hide that radius like I said, in a arc length. And we have to use that formula to pull that radius out. So there's little things like that we'll discuss and try to develop a skill for. But today, let's just work on finding the area of these things. So this one's not too bad. It's pretty straightforward. I want you to kind of try to avoid using your calculator, okay? Because I think there are some skills here that we need to refine. If I take this area here, this section, I'm going to go x over 360 times pi r squared, right? X over 360 times pi r squared. So what's x going to be in this particular question? It's a 72. Okay. R is the 15. So r squared would be 15 squared. What's 15 squared? 225. Okay. Now let's think about this. Last class I asked, okay, what's 72 divided by 360, and it blew their minds, and they grabbed their calculators. You might have heard me yelling. Let's think about this. If I had 36 over 360, 36 over 360 would give me what? 1/10, right? 1 over 10. 72 is twice as big as that, right? So that would give me 1 over 5, right? Okay. Try to develop relationships like that make sense to you, maybe using other numbers, and say, okay, well, 36 and 72 are halves of one another, might allow you to do that division in your head a lot quicker than grabbing my calculator. If I grab my calculator's going to give me what, 0.2 back, isn't it? And then I have to know that 0.2 is 1/5, because I want an answer left as a fraction here. So I get 1/5, okay, then times 225 times pi. 225 times pi. Okay. How many, if I multiply that out, it's 225 pi over 5. How many times does 5 go into 225? 45. So I'm left with 45 pi. Now, just like the other irrational numbers we've dealt with the radicals, we're just going to leave pi there as an implied multiplication. What we find out later on in other math classes is that when we leave that pi in there and we do something else with that area or whatever the expression is that involves pi, a lot of times the pi's will cancel each other out. There'll be a nice thing that occurs. So we just learn that process, learn to leave it in there. Is it okay? Okay. Let's do another one. So they don't always give them to you in regards to a picture. They might write it out in words. Okay. So here we need to know obviously what a radius is. I don't think there's any issue there. Sector bounded by a 45-degree minor arc. That might be a little confusing. A sector bounded by a 45-degree arc. What does the word bounded mean? Okay. Within bounds, would you say stuck by? Okay, within. When I see bound, I'm thinking constrained. Okay. Restricted. Does that make sense? Or within. Okay. So when they say bounded, it's basically giving you your limits, your segments and arc that create your sector. So when I draw my radius here of 4 inches, and I draw another radius of 4 inches, the minor arc that bounds this sector is going to be that arc right there. Is that okay with everyone? Minor meaning it's going to be smaller than 180. Okay? So it's 45 degrees. Is that okay? This blue shape here, like obviously we've got, let me color this in. We've got this red sector that we're trying to find the area for, right? The white region bounded by the blue arc, that is also a sector. Okay? Now, if me and Lex are sharing a pizza, I'm going to give Lex the red one, I'm going to take the white one, right? Okay? But it's still a slice of pizza, it's just a really big slice. Okay? So that's kind of the idea. All right? So both those things are sectors. It's just that other one is much bigger. It's got an angle here. This angle here is greater than 180, which is fine. So if I want to find this area, we're going to go x degrees over 360 times pi times r squared, right? So what's x? 45 times pi. What's r? 4 squared would be 16. Okay, this is kind of where I blew up on the last lesson. What's 45 divided by 360? 1/8. Okay. The way I asked it, and it was crickets. If you can't do that in your head, can you do 90 divided by 360? You know that's 1/4, right? You know 90 goes, or 360 and 90 will divide 1 to 4 or 4 to 1, depending on the order that you do it. Okay. Well, 45 is half of 90, right? Okay. So I should be able to fit twice as many 45s into 360 as I can 90s into 360. So that's where I get that 1/8 ratio, just without grabbing a calculator, without really doing any division, right? Just using previously known facts to help me get there. So this is 1/8 times pi over 1 times 16, right? Okay. What's going to happen with this 8 and that 16? They're going to cancel and leave me a 2 there, right? And a 1 down here. 1 times pi times 2 is 2 pi. 1 times 1 times 1 is 1. So 2 pi over 1 is 2 pi, right? Leave your answer in terms of pi, so we're done. Now, if they want it as a decimal, type that in your calculator, you get like 6.28 something, and then round to whatever decimal you need. Questions on that process? All right, so there's another type of problem that goes along with finding areas of sectors, and it's finding what we call the area of a segment. Okay? A segment is that little yellow sliver up there off of the edge of a circle. Okay? It's kind of like if we were to take the slice of pizza or slice of pie and cut the crust off. It's the crust. Try and find that area. Okay? Now, does anybody know, last class somebody knew this,
Yeah.
what you call this segment right here for a circle?
I can't remember, but it's...
Call that a chord. We're good. Okay? We call that a chord. Okay? Now, that yellow shape is bounded by the chord and by that arc, right? Now, those two measurements, there is nothing we can ever do with those two measurements to generate the area of that segment. Okay? So there's no way to generate the area of that yellow using those two values. Okay? So we don't have a formula for finding the area of a segment directly. Okay? However, what we can do, and this happens a lot of times, especially when we start talking about volumes, okay, and surface areas. We have to, good luck. We have to take and develop a kind of a plan before we go through and find the area of a segment. So every segment is associated with some sector. Does that make sense? So here is that sector that we're kind of walking ourselves through with. Okay? If you were to draw the chord from there to there, okay, and then highlight just the triangle that gets created, right? So that'll give me this triangle here. Does that make sense, everybody? If I wipe away that triangle, does it leave me with just the segment that I was interested in finding? And algebraically, wiping away something is subtraction, right? Okay. So that's the process that we're going to go through. Now, the hard part of these is finding the area of the triangle. Okay? The area of the sector is going to be just like the first two problems we did. That's going to be, here's X, here's R, plug in, evaluate, simplify, here's the area of your sector. Then you're going to have to go 1/2 BH for that triangle. And there's, just depending on what kind of triangle that ends up being, there's a couple different ways that you might address that. Okay? The one thing that you need to know is what kind of triangle that is. Sometimes It's isosceles. That segment right there and that segment right there are radii of the same circle, right? Radii of the same circle are always what's one other? Congruent. And so if they make up the sides of a triangle, then that must be an isosceles triangle, right?
Yes.
So, here's the thing. When we do this, now I'm going to draw that segment in right here.
That's a 90.
Okay. So what we're saying here is that this okay, so we're saying that blue, whatever color that is, okay, that triangle is going to be isosceles, no matter what, right? So this is always isosceles. Even out here, that triangle is isosceles now, right? Does that make sense to everybody? Okay. That color bothers me, so give me a second. Huh? Oh, I thought you were talking third person. Let's see here. Well, I'm going to... Yeah, I'm going to change that one. That's better. Alright, so. Like we got like a clean booger color and a dirty booger color. Alright. Alright, would you guys think, so if this is isosceles, so the angle that is created by your two congruent sides, or your legs, your isosceles triangle, that angle right there is called your vertex angle, right? Back in chapter 4, we've used this many times since chapter 4, but we know, or we should know, that every single time that you take a segment from the vertex angle perpendicular to the base of the isosceles triangle, that segment is going to be what to the base? Okay, so I heard a couple things. It is perpendicular, which is key, and it is an angle bisector up here. All right, and I heard somebody say that bisects down here. Okay, so those things are all things that we need in addressing the area of that triangle. Okay, so let me kind of clean this up just a little bit, get some intersection points in here. All right, so no matter where I move that angle, no matter how big I make it, and I look at the segment that's associated with it, this darker triangle is always isosceles, right? This is always a right angle where my cursor is. B to C and C, or sorry, B prime to C and C to B, those are always equivalent distances, right? Okay. What'd you tell me about this angle right here, Riley? Okay, so that angle is going to be half of 125, right? Okay. So it'll be 62 and a half. But here's the thing. This distance here, that black segment, that is going to be the what? If I go area, because I'm going to try to find the area of the triangle, right? Area is 1/2 BH. That right there is the height. That is H. Okay? Then what is this distance right there? That's B, right? Because remember, your base is by definition, it's the segment that your altitude is being drawn to. It's not necessarily the bottom or anything like that. It's the segment that the altitude is being drawn to. And we know for certain that blue segment is an altitude. Now, there are 3 altitudes of a triangle, and so there's 2 others that are out there, okay? for instance, in this picture here, this would be, that's terrible. The tablet was sideways. This would be another altitude, okay? But that's going to be very difficult for us to find that distance. Does that make sense, everybody? Okay? This H is going to be easier to find on the inside, so that's the one we're going to focus on. All right, so all those facts together kind of get us into doing a problem here, okay? Now, what they like to do is start you off with figures that have a 60-degree triangle in them, or a triangle that has a 60-degree in them, or a triangle that has 120 in it, or a triangle that has a 90-degree in it. Because then when I draw in that bisector from the vertex angle, it's going to take that 60 and make it 30. It's going to take this a 120 and make it 60. It's going to make a 90 into a 45. And basically what I end up with is special right triangles. Okay? So I can determine B and H real quick from that. But that's not always the case. So we'll do 3 or 4 of these, and when people think, well, that's what I do every single time, and then they get an angle or an arc that's 50 degrees. And then they forget, well, what do I do if it's 50 degrees? Well, if I break that in half, then it's 25. That's not a special right triangle anymore, so I use SOHCAHTOA, right? So we'll talk about that, but right now, let's just focus on this one here and trying to find that shaded segment area. And I'm just going to zoom in so I can draw on a little bit better. All right, so as you do this, every time that you see the fact that they want you to find this yellow segment, you want to set up a plan, and that plan should look like this. You're going to find the area of your sector. Okay? So your area of your sector is x over 360 times pi r squared. The next thing you're going to do is find the area of your triangle. That's 1/2 BH, right? What am I going to do with those things to find the area of my segment? We're going to subtract them. That's a sector. Okay, so the sector, remember the sector is now, it would be everything that is yellow, right?
Yes.
Everything that is yellow. So what would X be in that problem if I'm looking at everything that is yellow?
Everything.
It'd be 60. Over 360. Now, pi, what's R? 18. When I square 18, I get 324. Okay? What's 60 divided by 360? 1/6. Times pi times 324. How many times does 6 go into 32? Because I'm just trying to do 324 divided by 6. It goes in 5 full times, right? So I write 5 down. If it goes in 5 full times, that would be 30. Remove 30 from 32, you get 2 left, right? And a remainder of 4 in the ones place. So that gives you 24 left over. What is
4?
Yeah, 24 divided by 6 is 4. So 54 pi would give me what that reduces to, right? Okay. Yeah, you can use your calculators, but my hope is, guys, that eventually, that's what I was telling the last class, I started yelling at them. I wasn't yelling at them because of being mean, but, or that I was mad. I was just, at some point, most of you are probably going to have children at some point, right? No. And they're going to come to you and say, Mom, what's 324 divided by 6? And you're going to say, no! No! Empower your children with knowledge. Don't let them rely on just using calculators. Okay? All right, so we have 54 pi. Okay, that is the area of the sector. Now, trying to find the area of this triangle is going to be a little bit more of a task. Okay? So we are going to, let me just kind of erase this 60 real quick. All right, so when I draw in, I'm always going to draw in that altitude. Okay? So that's H, right? Yeah. Okay? Now when I draw that in, what did it do to the 60 down here? Cut it in half. So I get 30 degrees right there, 60 degrees right there, right? So what just developed? Okay, so that green triangle is a 30, 60, 90. Do we have the ability then, in that 30, 60, 90, of coming up with that red distance? Okay, now, why would I want to come up with that red distance? That is half of my base. So if I double that, I've now got B for my formula, right? So if this is 18, 18 is always what? I guess the hypotenuse is always what in a 30, 60, 90 triangle? 2n. So what is n then? N is 9, and that goes across from what angle in 30, 60, 90? 30. So that would be that distance right there, right? So that 9 is half my base. Go ahead. $18 is my hypotenuse. Okay? Yes. Okay? So this ends up being 9. This ends up being 9 as well. And what Jimin is saying right now is that shouldn't make sense because that was an isosceles triangle to begin with, right? By definition, with the radii of the circle, that's an isosceles triangle. But if you have a 60-degree angle in it, so an isosceles triangle with one 60-degree angle actually is equilateral. Yeah. So does it make sense that all those sides should end up being 18? Yeah. Okay. So that's B. No. So that's the next question. If this is like a 90-degree angle here, and this is 4, not all sides are 4. Does that make sense? Okay. It's only because of that 60-degree angle that was 18, and that's going to be 18. So base is 18. Now H. Okay. H is going to be right. It's your radical 3 side, your n radical 3 side. So it's going to be 9 radical 3. And I multiply that here. So that's H. Now what's half 18? 9. So now you have 9 times 9 times radical 3. What's 9 times 9? 81. 81. Yeah. So now we have 81 times radical 3. There's the area of your triangle. What do I do with the area of the sector and the area of the triangle to find the segment? Subtract it. So 54 pi minus 81 root 3. And that's the exact answer. And the directions, I kind of hit them a little bit, but you see them kind of come out the side of that picture. It says leave in terms of radicals and pi. And then I think it says something about transferring that into a decimal if we need to. Does it matter that you do the second one minus the first one? Well, I'm going to do the bigger one minus the smaller one, because I want my area to be positive, right? So if I were to do 81 radical 3 minus 54 pi, I'm going to get the same number, but it's going to be negative. So the sector is always going to be bigger than your triangle. So you go sector minus triangle always. Okay, now, we haven't talked about this formula yet, but you see it's up there on the whiteboard. An equilateral triangle has the formula s squared radical 3 over 4 defines area. What is S? What do you think S stands for? Side. They're all 18 here, right? Yeah. If I take 18 squared, I get 324, right? Yeah. How many times does 4 go into 32? 9. 8. How many times does 4 go into 4? Was that a little bit quicker finding that area? No. Yes. Okay. Now, that's a shortcut for just equilateral triangles, right? Okay. So in the next question, when it looks like this, okay, and I want to find the area of that segment, is that an equilateral triangle? No. Okay, it's got a 90-degree angle. Now, there is a shortcut to this, because we don't, in this one, if I want to find the area of my sector, okay, it's going to be 90 over 360, which gives me 1/4, right? So this is 90 degrees over 360, times pi, times r squared. R is 4 squared, I get 16, right? So what's a fourth of 16? 4. So I get 4 pi. Okay? Now I got to find the area of my triangle. 1/2 BH, right? Now, you can do this. You can do exactly what we did. You could split that, make that 45, So 4 would equal my n radical 2 side, right? N equals 4 over root 2. You can do all that. But that's dumb in this question. Why is that dumb in this question? It's extra work. But why is it extra work? What would be the alternative to this? Yeah, this is a right triangle, so each leg is either a base or a height, right? So then I can go here and go 1/2, 4 times 4, okay, which gives me 8, okay? Now, if I was going this route, think about this, just bear with me here real quick. This side here, this blue side, would be 4 over root 2. This would be 4 over root 2. Does that make sense? So then this base here is 8 over root 2. Does that make sense? So that would be B. I've got my 1/2 BH. This here is 4 over root 2 again, right?
I'll take your word for it.
4 over root 2. What's 1 times 8 times 4? 32. What's radical 2 times radical 2? 2 times that 2 right there would give me 4. What's 32 divided by 4? 8. Now, what do I do with those two numbers of 4 pi and 8 then? Subtract them. 4 pi minus 8 would be my answer. Because we're going to go 90, because it's x over 360 times pi r squared, right? So that x was 90. That's where the 1/4 shows up. Okay? Now, on your homework, guys, what if this angle wasn't 90? What if this was 80? Then that would be 40. Okay, right? And then to find that and that, you have to use SOHCAHTOA. You're going to use cosine and sine to find B and H. Okay? So those might be some alternative types of that product you might see on your homework. Okay? Finish that up. Let's do tomorrow. And then hopefully tomorrow we'll talk about probability a little bit.